Hello everybody. So one of the things that I found out from the survey is that you guys like videos and explaining things as you go through it. So that's what I'm going to do here. Just as a warning, this is going to be a pretty boring video. I'm just going to do the answer key and kind of take you through my thought process as I go through it. So let's get into it here. The first one, name 2 things to look for in regression when deciding which model is best to look for. Which model is best? That would be the highest R-squared value, the highest coefficient of determination, and a residual plot with no clear pattern. So you want to have no U-shape or anything like that. Problem 2, 6 cats were randomly selected. Each cat was weighed and had its tail length measured. Results are below. The goal is to predict the height, and then we want to determine which of the 3 equations is best. So let's start with the linear model. I have already put in the data into the calculator here. So I am now going to go to Stat, Calc, run the regression, which is 8 for linear regression, and I get negative 11.98 plus 2.119x, and the R-squared value is 0.927. Okay, let's do exponential next. Stat calc, exponential regression. I get y hat equals 2.783 times 1.138 raised to the x with an R-squared value of 0.970. So far, exponential is winning. Let's see if it can hold on here as we go into power. Stat calc, power regression, and there it is. Y hat equals 0.2061 times x raised to the 1.68 with an R-squared value of 0.959. So which one of these is the winner? That would be our exponential model. So our exponential model, just to put it out with words inside the variables, this would be the cat weight, which is our response variable. We know that because the goal is to predict cat weight, which means that's the y based on tail length, which is the x, equals 2.783, 1.138 raised to the tail length. Now we're going to confirm that it's the best, possibly among other models that we haven't considered, by looking at the residual plot. In order to do a residual plot, we actually need to go back in and rerun the regression. Because the power regression was the one I most recently did, it's going to think that we're still using that model when it does the residual plot. So if we go into Stat, Calc, scroll on down to exponential regression, I'm just going to rerun it. I'm not going to do anything with it other than having the calculator know this is the regression equation to use. Then we're going to go to Stat Edit, go over to L3, hit Enter, and if I hit second stat, which is list, down here is the resid button. It knows to use that most recent regression equation, and those are their residuals. Now let's make a residual plot. Going over here, turning it on, that's the scatter plot. My x-list is L1, my y-list is L3, that's where the residuals are. So I am now going to do the official zoom of statistics, zoom 9, and there it is. So it looks like I got one value there, up there, there, oopsie, maybe there and there-ish. So that's what the residual plot looks like. There's no clear shape here. So exponential is the best model available. Confirmed by the highest R squared of the group. Use the best model to predict the residual for cat number 6. That would be this cat right here. That cat had a tail length of 15. So let's see what happens when we put in 15. $19.348. Because we use the equation, this is the predicted value, so that is our y hat value. Residual, you're in AP Stats, it's actual minus predicted. The actual weight of cat 6 was 18. The predicted weight was 19.348. So this cat came in a little bit underweight from what we'd predict. Negative 1.348 pounds is the residual. Page 2. So this is a scatter plot of weight versus length, and if we look through this, this is just a regular linear regression model. So they're testing to see if this is linear. I'm just looking at this here. That does not really look linear. And then when you do a residual plot, it is clearly not linear. So the answer to this is no. The residual plot makes a clear U-shaped pattern. Okay, now we're going to take a look at the natural logarithm versus natural logarithm. So natural logarithm of one variable, natural logarithm of another. That is a power regression. That's what that part of the problem is telling you. If you take the log of both variables, it's a power model. So it's clearly more linear. Does this data suggest that the length can be modeled by exponential or power? Power function is the answer. Since both variables were transformed using logarithms. Next. Okay, so this one up here asks you to match the left-hand column with the right-hand column. So an exponential regression of y versus x, power regression of y versus x, which one would have the same r squared values? Coefficient of determinations r squared. So would an exponential regression of y and x have the same r squared as a linear regression of y and x? No, we're not, unless there's some crazy situation going on. An exponential regression is when you take the log of y but leave x alone, which is like what that last one here is. So this guy should be connected down there. Power regression is when you take the log of both variables, like this one right here. So that goes with that. And that problem's over. Moving on to the next one. So we have the costs of a tuition versus year. I didn't see any logs there, so this is just a regular linear regression. Based on the residual plot, which the following statements must be true. Tuition costs decreased from 1976 to 1982. We don't have an equation. We don't know what the slope of this is. We don't know if this is true or not. I would guess that tuition increased, but there's no evidence of this, so we're going to say we don't have enough information for that one. This regression equation would underestimate the cost in 1992. 1992 is in this section here. If the residuals here are all negative residuals in general in that section, that means that the actual value is lower than the predicted value. So the regression equation would underestimate tuition costs in 1992. The regression equation is like this line right here. This line is above. it's an overestimate at that exact place because the actual values were below it. So if this had said overestimate, this would have been correct, but this one, unfortunately, is also wrong. The relationship between tuition cost and year is nonlinear. This is a clear U-shaped pattern. That implies that the data is not linear, which would make this one true. So I'm looking for 3 only, which is choice C. Number 8, the scatter plot of log tuition versus year shows a strong positive linear pattern. Notice there's no log there. That tells me that this is an exponential regression they're running here. Which one of the following conclusions can be drawn? The scatter plot of log versus log will be strong positive. We don't know that for sure. It could be, but we don't know. The residual plot for log tuition shows a clear curved pattern similar to the one above. We don't know that, and it's probably not true. The relationship between tuition cost and year can be modeled by a square root function. The relationship between tuition cost and year can be modeled by an exponential function. That's the one we're looking for. And our winner, power function, would have been log of both. Quadratic would have had, or square root would have had some kind of squaring transformation, not logarithms. Last page. So we have a computer regression. This is a mini-tab printout, which the following is the correct equation from the analysis. So we have log of tuition cost and years. This is an exponential one, but we're looking for the one that has log of tuition and regular year. So we can cross off all these ones because those all have log of year. This one doesn't have log of cost, so I can tell right away without even looking at the numbers that that must be the right answer since that has these variables in it. Okay, final question. The lifespan for various mammal species has been related to average size. A typical meerkat weighs about 0.9 kilograms. What is the predicted lifespan of a meerkat in captivity according to this equation? So we have this weight here, about 0.9 kilograms, and we want to find out if that is L or M. So the lifespan is L, that's not a lifespan. Average size, M, that is a size. So that is an M value. 2.468 plus 0.2 times the ln of 0.9. Let's just throw that in the calculator here. I am getting 2.447. Of course, that is equal to the ln of L. In order to get L by itself, ln is really log base E of L. So using log properties, this would become L equals E raised to 2.447. So I'm going to do E raised to the answer. And I get 11.553. Which is choice C. And that finishes our assignment here. I hope you enjoyed the video, and email me if you have any questions. See you later.